Hey everyone, and welcome to PyTorch, Deep Learning and Artificial Intelligence. Now this is one of the most exciting courses I've ever made. I've been making these deep learning courses for a long time, before PyTorch was even invented. So it's been quite a journey for me to see how this field has evolved in the past few years. And guys, it's been moving quick. The best practices and guidelines you'll learn in this course are the latest and greatest. This stuff did not even exist when some of my previous deep learning courses came out. Things like the best way to train your neural network to architecture decisions. Thanks to the hard work of deep learning researchers all around the world, I've been able to take what they've learned and bring that information to you. This course is designed to be a beginner to advanced course. So you don't need a lot of math and background knowledge, but of course, if you're into that sort of thing, I certainly have resources for you. We're going to start by looking at basic machine learning in the form of a neuron, the fundamental building block of neural networks. From there, we are going to jump right into neural networks, the thing that started it all. Luckily, with PyTorch, you don't need a lot of heavy theory unless you want it. The PyTorch API already implements a set of composable building blocks, so you can focus on building cool things rather than debugging and mathematical equations. Next, we're going to look at convolutional neural networks, which are specialized neural networks for computer vision. Then we'll look at recurrent neural networks, which are specialized neural networks for sequence data, such as time series, text, speech, and DNA. We'll even apply RNNs to stock prediction. This is one of my favorite exercises from this course because it teaches you what 90% of other people are doing wrong. If you've ever used an LSTM for stock prediction before, or taken a class that promised to teach you, you'll definitely want to watch this. Because PyTorch has a modern and easy-to-use interface, it makes building extremely complex things much easier than they used to be. Here are some example applications. First, we have GANs, which stands for Generative Adversarial Networks. These are a new training paradigm which allow you to use deep learning to generate beautiful photorealistic images. What's absolutely crazy about this is that the images you are looking at now are of people that do not actually exist, but it doesn't stop there. Deep learning has been applied in the field of reinforcement learning, which excels at tasks that take multiple steps to complete, like playing a video game. Deep reinforcement learning agents have beat world champions in the strategy game Go and in modern video games such as CSGO and Dota 2. These are things we wouldn't have dreamed of just 10 years ago. Of course, if that's not enough, we still have more. Deep learning powers state-of-the-art natural language processing applications, such as speech recognition and machine translation. So whenever you talk to your phone and it figures out that you want to say, order a pizza, or set an alarm tomorrow for 6 a.m., that's speech recognition using deep learning in action. Neural machine translation has significantly enhanced the capabilities of language translation in the recent years. With students in 200 countries around the world, I've made use of this great technology more than once. And guys, I could go on. There's self-driving vehicles, object detection, facial recognition, deepfakes, synthesizing speech so you can have a phone conversation with a robot. So if you want to learn how to use the world's fastest rising deep learning library, this course is for you. Thanks for listening, and I'll see you in the next lecture. In this lecture, I'm going to give you an outline for the rest of this course. First, I want to give you a brief summary of what PyTorch is all about, in case you've had previous experience with TensorFlow or other deep learning libraries such as Theano. So in the beginning, there was Theano. Theano was a significant improvement over what was being done previously for two major reasons. Number one, for reasons you'll learn about later, writing neural networks from scratch involves doing a lot of matrix calculus by hand and then copying those equations into code. For those of you who took my first deep learning course, you know how difficult this can be. The Theano library was the first to innovate in this area using automatic differentiation, or AutoDiff for short. What that means is you don't have to write down calculus equations, since the computer will do that for you. And number two, there's a lot of math that has to happen in a neural network, and this takes a lot of time. meaning you'd have to wait hours or even days or weeks to train your neural network. The Theano library was the first to innovate in this area by making use of GPUs, which were originally designed to improve the performance of PC games. One of the downsides of older libraries such as Theano is that you have to build everything by yourself. This can really slow you down, especially if it's your first time writing certain components. You'll not only have to write each component on your own, you'll also have to worry about them being right. If any single component you wrote is wrong, then it could make your entire program fail. On top of that, in the previous years, it was announced that the Theano library would no longer be maintained. What about TensorFlow? TensorFlow is a pretty popular library, thanks to the fact that it's backed by Google, who at this point kind of run the internet. TensorFlow used to be really messy, in fact probably more so than Theano, but now, in version 2.0, it uses the Keras API, which is the total opposite. It's very high level and very simple. But there is a downside to very high level and very simple APIs. They make it very easy to do common things, but hard to do uncommon things. PyTorch, on the other hand, has been slowly gaining adoption in the field of deep learning, thanks to the fact that it's relatively easy to do common things and still easy to do uncommon things. For this reason, it's been extremely popular in the research community, who, by definition, do lots of uncommon things. That's their job after all. PyTorch is developed mainly by another internet giant, Facebook, specifically the Facebook AI Research Lab. As with all deep learning libraries, PyTorch is supported by GPU acceleration and has automatic differentiation, so there's no need in this course to use tools like calculus and linear algebra to derive backpropagation. If you hate math, then you should feel very lucky. In fact, we won't discuss backpropagation at all, despite the fact that it's really the main ingredient that makes everything work. This, combined with the fact that a lot of the basic building blocks are already built for you, are some of the major advantages, which are going to allow us to blast through each section very quickly. In the past, it was necessary to focus on each architecture one at a time, with RNNs being the most complex to implement. These days, ANNs, CNNs, and RNNs can be implemented in just a few lines of code. Alright, so how is this course structured? First, before we even begin discussing deep learning or any type of statistical modeling, we are going to look at a new coding environment which I really like, called Google Colab. Google Colab is basically Jupyter Notebook hosted by Google, but with a lot more bells and whistles. Personally, I have never been a fan of Jupyter Notebook, since it seemed to have more disadvantages than advantages. However, Google Colab is a different beast. It's hosted by Google, so you don't have to use your own computing resources. It's free, so it doesn't matter if you have a slow computer or a fast computer, everyone has the same access. It gives you free access to the GPU and TPU for orders of magnitude faster training and inference. And finally, most of what we need is already installed, so you don't have to waste any time installing libraries yourself. Once you've done that, we are going to go through the fundamental architectures involved in deep learning. Believe it or not, this all starts with linear regression, the line of best fit you learned about in high school physics. We'll see that with just one little change, adding the logistic function on top of a linear model, we will get a neuron. This covers the two major types of supervised learning, classification and regression. Once you know the basics, it's time to get started with deep learning. The first deep learning architecture you'll learn about is the artificial neural network, also known these days as the deep neural network. Although neither of these names really do a good job of differentiating it with other architectures. Next, we'll dive into image processing with convolutional neural networks. You'll learn about convolution and how this works to create neural networks that are specially designed to achieve better performance on images and other physical signals. Next, you'll learn about recurrent neural networks, which specialize at working with sequence data. Unlike my previous courses, where we used RNNs mostly for natural language processing, we are going to start with time series forecasting. This is going to let us cover a lot of ground that many other courses simply skip over entirely. In particular, we're going to cover the difference between the wrong way to do a time series forecast and the right way. We're going to look at several time series that simple models like linear regression can and can't solve, as well as several time series that slightly more complex models like the simple RNN can and can't solve. For the more difficult problems, we'll see how the LSTM achieves superior performance. And so you'll see firsthand why LSTMs are useful, rather than me just telling you and you accepting it as fact without observing it for yourself. The next example is one of my favorites in the course, which is on stock prediction with LSTMs and RNNs. I think most of you will find the contents of these lectures very surprising. If you've ever learned about stock prediction with LSTMs in the past, be warned. Most other instructors are doing this the wrong way. In this course, I'm going to teach you why it's wrong, how to correct it, and what some of the real obstacles are in stock prediction. The first major part of this course is about the fundamental architectures in deep learning, while the second major part of this course is focused on applications. As a side note, if you want to just skip the rest of this lecture and move on with the rest of the course, that's fine too. The first application we will look at is natural language processing, specifically with text documents. You'll see how we can use deep learning for text classification, which is the type of task you would use for spam detection, sentiment analysis, and so on. We'll also look at embeddings, which are deep learning's method of dealing with categorical data. Embeddings will lead us to our next application on recommender systems. Now, it might seem weird to think that natural language processing would be somehow related to recommender systems, but hopefully in this course you will learn about the hidden connection between these two different fields. Recommender systems is all about how to optimize the products or items that you recommend to your users. Facebook, Amazon, and Google have been using recommender systems to improve their profits by the billions. When you go to Amazon.com, it is full of recommended products for you. Facebook's newsfeed and your Instagram feed are both recommendation lists. Google's search results, advertisements, and the YouTube sidebar are all examples of how Google uses recommendations. In short, recommender systems are one of the most practical business applications of deep learning, and one that can be used in a pretty straightforward manner to improve your profits. This is in contrast to, say, natural language, where it's not exactly clear how that would directly tie into how much money your business makes. Although, it's already a fundamental part of our day-to-day lives, so don't discount it just yet. The next application we'll discuss was a game changer for deep learning. If you've taken any of my deep learning courses in the past, you know that training a deep neural network takes time, lots of time. You might end up waiting hours or even days or possibly even weeks. Luckily, machine learning engineers have found new ways of allowing us to build on top of the work of others. The idea is, companies like Google or Facebook or university research groups will train large neural networks on humongous datasets, such as ImageNet, which contains over 1 million images. That's not the kind of thing you can feasibly do on your home computer. Using transfer learning, what we can do is take just a part of their neural network and combine it with our own neural network designed for a specific task that we want to do. Results have shown that this is an easy, and more importantly fast method of building state-of-the-art deep learning models. In just a few seconds, you can integrate the power of bleeding-edge neural networks into your own applications. Next, we have GANs, or Generative Adversarial Networks. This was named as the most interesting invention in machine learning in the past 10 years by Yann LeCun, a deep learning pioneer who is now the chief AI scientist at Facebook. GANs are all about generating images using a system of two neural networks. One that generates the images, and one whose job it is to discriminate between real and fake images. Using this pair of neural networks, they both help each other improve. So the discriminator becomes better and better at recognizing fakes, while the generator becomes better and better at creating realistic images that cannot be differentiated from fakes. When people think about deep learning, they don't often think about how neural networks can be used to generate things, but rather just how neural networks can make predictions on things. Predictions are nice, but generating things opens up a whole new world. Recently, Google announced a conversational AI, where you could have a personal assistant do something like call a restaurant and make a reservation for you. But that personal assistant is not a person, it is a robot. All of its speech is generated by a computer. Another exciting application of deep learning is in reinforcement learning. Usually, deep learning is used to create models with a static input and output. For example, you put in an image and it tells you what this image is of, like a car or a truck. Or you put in an email and your neural network tells you if it's spam or not spam. But some tasks require multiple steps, which requires having some long-term strategy and keeping track of state. For example, if you're playing a game like Super Mario, you can't just look at a still image of the game and decide what to do. Instead, you need to have a long-term strategy. You have to know that you should walk forward to reach the flag for that level. You have to know that if an enemy is walking towards you, you have to avoid it or attack it. And also, you have to have proper timing in doing so. This is what reinforcement learning is all about. To summarize, the outline of the course is like this. We can split it into two parts. Part 1, architectures, and Part 2, applications. In Part 1, we discuss the fundamental architectures such as linear models, ANNs, CNNs, and RNNs. In Part 2, we discuss applications such as NLP, recommender systems, GANs, transfer learning, reinforcement learning, and possibly more. Thanks for listening, and I'll see you in the next lecture. In this lecture, we are going to discuss where to get the code for this course. This course will be a little bit different compared to my previous courses because we are going to mostly make use of Google Colab. However, there are still a few things which I'm going to include in the course repository, such as links to relevant papers and a few Python scripts that you'll want to run locally. So in order to get the links to the Colab notebooks, you can find these links in a document I've attached to the Extras section. When you click on one of these links, it'll take you directly to my Colab notebook. Now, because this is a shared notebook, you won't be able to do much with it. So what you probably want to do is make a copy of the notebook in your own Google Drive, or simply download the notebook and run it locally. As always, Python code is Python code, no matter what environment it's in, so you don't even need Notebook per se. Just save everything to a Python script, and you can run the same code from the console. So as usual, for the course repository, you'll want to go to github.com/lazyprogrammer/machine learning examples. In order to get the code, please don't try to copy and paste it from the web page itself. Use Git instead. I've seen students do this in the past, and it frequently causes errors. So just use the command git clone and then my GitHub URL. Also, I would recommend not forking the repo, as this makes it harder to get updates, and I'm updating the repo pretty much constantly, so you don't want to be stuck with an old version. In addition, some students have been confused by forked repos in the past, thinking they had found the correct repo for the course when in fact they had not. So for the sake of future students, please do not create your own fork. And if you're a student searching for the code right now, please double check that you have the correct GitHub URL and not someone else's out-of-date fork. As most of you know, one of my number one rules for learning is to write your own code. Machine learning is all about programming. This is not a philosophy course. Everything you learn in this course involves hands-on work. So whether you are deriving equations or writing code to implement those equations, you're going to be very hands-on. You should never find yourself asking, how would such and such work theoretically? If you ever have a question like that, it is always better to answer it just by writing some code and doing an experiment. Machine learning is about experimentation, not philosophy. Remember that the pattern we are always going to follow is to go from theory to code. First, we discuss what we are doing, that's the theory. Then we implement that thing in code, that's the code. So you should never be confused about what we are doing in the code, because we are always just doing the thing that we just talked about. Sometimes I come across students who try to start the course by watching a lecture in the middle of the course. Usually they end up lost. I don't want you to get lost. So most of the time, if you want to make sense of what you're watching, you have to watch the lectures in order. The lectures build on each other and they tell a story. If you don't watch them in order, it's kind of like trying to read a book by picking random pages in the book. Of course, if you're looking for something specific, that might be a good strategy, but for most of you, that's not going to be the case. And remember that whatever we're doing in the code is not coming from nowhere. We're just doing what we said we were going to do in the previous lecture. Ideally, you're always trying to code by yourself, so if you want some tips for how to get started with that, I would recommend watching How to Code by Yourself in the appendix. Finally, I want to remind you that whatever coding environment you use, it is 100% your choice. A lot of people tell me they like Jupyter Notebook. Well, if you like Notebook, then you should be using Notebook. Remember that Python code is Python code, no matter where it is. There's no difference between Python code in Jupyter Notebook and Python code in the console. The same Python code would work the same in both environments. Remember that in these videos, all you're seeing is just code on the screen. There's no difference between me using a text editor or even putting the code in slides. You can't touch it or interact with it anyway. So it doesn't matter what I use, because that's not suggestive of what you should use. If you find the terminal very scary or intimidating, then maybe you don't want to use it. That's okay. Of course, the terminal is actually very useful, so I would recommend working your way up to being comfortable with it. But for this course, when you're writing Python code, you can choose your own environment. The same code works everywhere.